Alright, this is a third video on chemical nomenclature. It's being done on an iPad, so the quality will be a little bit lower than before. In class, we've already looked at, and in previous videos discussed, several types of nomenclature involving ionic compounds. We looked at binary ionic compounds type 1, so those are ionic compounds with a metal bonded to a nonmetal, just two elements, binary, and the metal cations there have only one possible charge, so something like aluminum chloride. We've looked at binary ionic compounds type 2, again an ionic compound, a metal bonded to a nonmetal, only two elements involved, binary, but now the metal cations have more than one possible charge, and therefore the names include Roman numerals to indicate the charge. So copper 2 chloride, for example, would be a binary ionic compound type 2. When we say copper 2 chloride, the 2 is telling us that the copper's charge is 2 positive. Copper has more than one charge, so the name has to tell you which charge you mean. The third type involved complex or polyatomic ions, and there's a whole list of these on page 6 of your data booklet that we asked you to memorize to make it easier, but these are ionic compounds involving groups of atoms that collectively have a charge. For example, NO3 with a minus beside it is called nitrate. If we bond that with the copper 2 plus that we just talked about, you'd get CuNO3 2, and this would be called copper 2 nitrate. 2 because the copper's charge is 2 plus, and copper is what type 2 cation, and nitrate is the name for this complex ion. So those are things that we've already looked at. In this video, we're going to now look at hydrated ionic compounds and binary covalent compounds. So we'll finish up the ionic compounds with hydrated compounds and then move on to a different kind of compound. So let's begin. Hydrated ionic compounds. We've done a lab on these already in the course. We've talked about them. A hydrated compound, a hydrated ionic compound, is a salt. Okay, the word salt is important. Any ionic compound can be called a salt. It's another name for ionic compound. But in a hydrated compound, a hydrated salt, there are water molecules trapped within the solid crystal structure. In our earlier grade 9 science course, we saw crystal structures like sodium chloride, which was cubical, and potassium nitrate, which was needle-shaped. Neither of those crystals had water trapped within them, so those were not hydrated salts. However, in many examples of salts, water does get trapped within the crystal structure, and it turns out that in those situations, there's a characteristic number of water molecules trapped for every formula unit of the salt. We'll see an example down below here. Copper sulfate, copper 2 sulfate, when it evaporates from water, you tend to find that, when water evaporates leaving behind the crystalline solid, you tend to find 5 water molecules trapped within the crystal for every CuSO4 formula unit in the salt. So 5 waters for every copper sulfate are trapped within a copper 2 sulfate salt crystal. When we name hydrated compounds, hydrated salts, we simply use prefixes, and these prefixes need to be memorized. These prefixes are used to tell us how many water molecules are trapped within the crystal for every formula unit of salt. If there's 1 water molecule trapped, we'll say monohydrate. 2 water molecules, dihydrate. 3 trihydrate. 4 tetrahydrate, etc. If there were 10, we would say decahydrate. Take a look at the 2 examples shown here. CuSO4 dot 5H2O. Notice that we use a dot, not a decimal point, although when you're doing a web assignment online, you will use a decimal to indicate this, but when writing it out on paper, you put an elevated dot like this between the salts formula and the water molecules associated with it. So this, if we were to name this, we would first name the CuSO4. So using what we've already learned, copper, and then SO4 is sulfate. However, copper has more than one charge, so we need a Roman numeral to tell us which charge this is. I know from my memorizing that sulfate is 2-, and since there's one copper bonded to it, the copper must have been copper 2+. Copper also could be copper 1+, but in this situation it's copper 2+. So we're going to call this copper 2 sulfate. 2 because copper is 2+. Then we see the dot 5 H2Os, which means there's 5 water molecules trapped for every CuSO4, so we add the last part of the name, pentahydrate. Penta meaning 5 water molecules, and hydrate to talk about the water molecules. So copper 2 sulfate, CuSO4, pentahydrate, dot 5H2O. In the next example, MgCO3 is magnesium carbonate. Okay, that's a complex ion again. CO3 2- is carbonate. Notice in this situation we don't need to use a Roman numeral because magnesium has only one charge. Magnesium is an alkaline earth cation, so therefore its charge is going to be 2+. So I didn't need to say magnesium 2 carbonate because it has to be magnesium 2. There's no other possible charge. The last part of the name, decahydrate, because there are 10 water molecules associated with it. Deca is the prefix for 10. So make sure you know these prefixes. We're going to use them not only for hydrates, but as we'll see in a minute, for covalent compounds as well. Here are some examples. You can pause the video and see if you can get these yourself. Take the first two names and see if you can write out the corresponding formulas, and then take the last two formulas and see if you can write the corresponding names. So the first one, copper 2 fluoride. Copper 2 means we have Cu2+. Fluoride, ending in IDE, means this is not a complex ion. It's just a simple ion, fluorine, with a charge. It's got to be negative, fluoride. And as a halogen, a member of the halogen family, its charge is -1. So Cu2+ bonded to F- means we must have CuF2 as the formula for copper 2 fluoride. But then there's a tetrahydrate. Tetra means 4, and hydrate, of course, refers to water, so we'll add a dot 4 H2O. CuF2 dot 4 H2O, copper 2 fluoride, tetrahydrate. Calcium nitrate, calcium Ca2+, 2+ because I recognize that it's an alkaline earth metal with a charge of 2+. Nitrate, ATE, is a complex ion, and I've memorized that, NO3 with a minus charge. The calcium here is 2 positive, while the nitrate is only 1 negative, so to balance the charge we need 2 nitrates to bond with the 1 calcium. If you've got more than one complex ion, you put the complex ion in brackets and you indicate the number outside the brackets. So 2 nitrates bonded to 1 calcium. Trihydrate, tri means 3, so dot 3 H2O. There's the formula for that salt. The next one we're going to work backwards. Write the name, Mg, magnesium, and SO4 2- is sulfate, so that's magnesium sulfate. We do not need a Roman numeral Again, because magnesium is a type 1 cation, it has only one charge, 2 positive. And then we see 7 H2Os, so the prefix for 7 is hepta, and then the water, heptahydrate. I'm going to run out of room here, but see if I can squeeze it in. Heptahydrate. The last example here, iron chloride, but a warning bell goes off because iron is a type 2 cation. It has more than one charge. Iron can be either 2 plus or 3 plus. Let's see what we have here. We can tell there's 2 chlorides bonded to the iron, and I know from a periodic table that chlorides, as a member of the halogen family, are -1. There's 2 of them, which means this iron must be 2 positive. So this guy is actually iron, Roman numeral 2, that's its charge, 2 positive, chloride. And then it has 1 water molecule attached. The prefix for 1 was mono, so monohydrate is added to the ending of the name. So iron 2 chloride monohydrate is the name of that compound. So hydrated salts. As we saw in our lab, if we heat the hydrated salt, the water can be driven away, and what would be left, CuF2 or CaNO3, that what's left is referred to as the anhydrous, whoops, let me erase that, anhydrous salt. ANHYDROUS. So anhydrous salt is the salt having lost its water, literally no water. Okay, so magnesium sulfate, just the MgSO4, would be the anhydrous form of that third salt. Iron 2 chloride would be the anhydrous form of the last salt. We're now going to leave behind ionic compounds. Ionic compounds, we remember, are made of ions, a cation bonded to an anion. It's electrostatic attraction, opposite charges attracting, which hold those things together. That's the ionic bond. They're made of a metal, almost always, bonded to a nonmetal. Okay, and there can be complex ions or simple ions involved. We're going to move on to look at covalent compounds, binary, so we're looking at compounds now made of just non-metal elements. So now there's no metals involved. And in these situations, they're called covalent because they share, that's what co means, valence electrons. That's what valent refers to. So instead of giving electrons and taking electrons, leading to the formation of ions, now the atoms share electrons. Because they're sharing, there are no ions involved. This is really important. There's no ions in these compounds, there's no charges to cancel out. Now that may seem nice, we don't have to worry about charges, but the problem, if you think about it for a minute, is that the charges are what told us how to write formulas up till now. If there was a 2 plus ion bonded to a 1 minus ion, then that meant we needed 2 of those 1 minus ions and 1 of the 2 plus ion. Now there are no ions, so there's no charges. So how will we know how to write a formula for a covalent compound? The answer is that we'll use those same prefixes that we just learned for hydrated compounds, and these prefixes will be used to tell us, in the name of the compound, how many atoms of each element we need to include. For example, CO2, there's 1 carbon and 2 oxygens, so its name will be carbon dioxide. Now notice here that technically you might have thought, well, there's 1 carbon, so maybe we should have said monocarbon. Mono is the prefix for 1. However, the prefix mono is never used on the first element in the formula. So CO2 is not monocarbon dioxide, it's just carbon dioxide. Now notice I could tell from the formula that I needed to use prefixes like di because carbon and oxygen are both nonmetals. When I only have nonmetals, no metal is involved here, then this is a covalent compound. That's the clue that we need to use prefixes in its name. CO, again, two nonmetals, carbon, oxygen. So we're going to use prefixes in the name. There's one carbon and one oxygen. So the one carbon will just be called carbon. The one oxygen will be called monoxide. Monooxide shortens to monoxide. So that's one carbon, one oxygen. Again, we don't use mono for the first element in the formula, but as you can see there, we do use it on the second element. N2O, again, has a nitrogen bonded to an oxygen, which means two nonmetal elements are involved, so this is just a covalent compound. Therefore, we have to name it using prefixes. It's got two nitrogen atoms and one oxygen atom. So the name will be dinitrogen, two nitrogens, and monoxide, one oxygen. Last example, SO3, again, has just nonmetal elements, so it's a covalent compound, and it's got one sulfur, three oxygens. So sulfur trioxide will be the name. Now, covalent compounds are also known as molecular compounds. That's because if you were to magnify the substance down to the point where you could see atoms, you would see molecules like this of the compound. You'd see a molecule of CO2, a molecule of CO. Ionic compounds are not like that. An ionic salt, take sodium chloride for example, if you magnified it, you'd see something like this. Sodium bonded to chloride, but then another chloride beneath the sodium, another chloride above the sodium, another chloride to the left of the sodium. In 3 dimensions, there'd be another chloride behind it and another chloride in front of it. Then there'd be a sodium here, a sodium here, a sodium here. Notice as you magnify sodium chloride, an ionic compound, there are no individual molecules of NaCl. Instead, this sodium in the middle is bonded to one chloride, two chlorides, 3, 4, and then 2 more that I didn't show behind and in front. There's 6 chlorides bonded to that one sodium. If you picked out one chloride ion, you could find that there are 6 sodiums bonded to that one chloride. There are no molecules of NaCl identifiable within that salt's crystal structure. However, because there's only one sodium for every one chloride, we'd write the formula NaCl. It's not a molecule of sodium chloride, we call it a formula unit of sodium chloride. Covalent compounds, however, if magnified down to the atomic level, you do see 2 atoms of nitrogen bonded to 1 atom of oxygen in what is a particle separated from any other particle, so it's a molecule of N2O. Similarly, you'd see an atom of sulfur bonded to 3 atoms of oxygen in what would be a molecule of SO3, sulfur trioxide. So covalent compounds are also called molecular compounds. Try a couple of quick examples here of naming with covalent compounds yourself. Pause the video and see if you can get these. So SO2, did you stop and consider that it has 2 nonmetals, sulfur, oxygen, therefore it must be covalent? If it's covalent, then we can name it using prefixes. Sulfur, because there's 1 sulfur atom to begin with, and then dioxide, because there's 2 oxygens. P4O10, again, stop and convince yourself that it's covalent. It's got phosphorus bonded to oxygen, so it's got two nonmetals. So we're going to name it using prefixes. 4 phosphorus atoms, so tetraphosphorus, and 10 oxygens, deca or dec oxide, to contract the deca oxide. So notice we name the first element as though it were a cation. Its name is the same as the element name, but the second name is always named as though it were an anion. It's named with that ending IDE. Phosphorus pentachloride, working backwards, there must be 1 phosphorus and 5 pentachlorides. Dinitrogen trioxide, so there must be 2 nitrogens, dinitrogen, and 3 oxygens, trioxide. Okay, so know what those prefixes represent. We'll finish with some mixed nomenclature. This is from a worksheet you'll be doing later. In the first column, put the letter I if it's an ionic compound, or M if it's a molecular compound. Another possibility, which we'll look at later, is that it could be an acid, and none of these examples will be acids, so we don't have to worry about that. If you see the formula, write the name. If you see the name, write the formula. So the first compound, I see a metal, aluminum. Have a periodic table beside you if you're not sure of what the metals and nonmetals are. Metals are on the left side of that staircase, so aluminum is a metal. And then I see the complex ion, hydroxide. A metal with nonmetals, this must be an ionic compound. Therefore, we name it, as we did at the start of the unit, as just the metal, aluminum. Now, aluminum is not a type 2 cation. It has only 1 charge, so we don't need to put a charge as a Roman numeral. And then we just name the anion, and OH is hydroxide, so aluminum hydroxide. Sodium sulfate, decahydrate. There's several clues in that name that this is also an ionic compound. Sodium is a metal, so there's clue number 1. Sulfate is a complex ion, so there's another clue that it's ionic. And decahydrate means this was a hydrated compound, and only ionic compounds are hydrated like that. So let's name it. Write the formula. Sodium is Na with a charge of +1. Sulfate is SO4 with a charge of 2-. So sodium sulfate would be Na2SO4. 2 sodiums for every 1 sulfate. Decahydrate means there are 10 deca water molecules, hydrate, associated with it, so dot 10H2O. The next example, similarly, there's a metal, so this must be ionic. It's got a complex anion, so again it must be ionic. And it's hydrated, so again it must be ionic. There's 3 clues there that it's ionic. So again, the sodium's charge is +1, Na+. Nitrate is NO3 -1. It's a complex ion. Since sodium is +1 and nitrate is -1, we need just 1 of each. So 1 sodium, Na, and 1 nitrate, NO3. Hexa means 6. So hexahydrate, there are 6 water molecules associated with that. The next example, working the other way now, has aluminum. That's a metal, so again this will be ionic, bonded to sulfate, SO4. So this is definitely ionic. Right, now aluminum sulfate is going to be the name. We just name the cation, aluminum, and then we name the anion, sulfate. Again, double check, aluminum is not a type 2 cation, so we don't need to say what its charge is. calcium chloride hexahydrate. Again, that's ionic. Lots of ionic examples here. Calcium, Ca. Whoops, I just changed my pen there by mistake. So calcium, Ca, and calcium's charge is 2 plus. Chloride, Cl, has a charge of -1. So 2 plus and -1, CaCl2. Notice because it was chloride with a De, I know that that was a simple ion, not a complex ion. There's only 2 or 3 complex ions that end in "ide": hydroxide, cyanide, hydrogen sulfide. Otherwise, if you see "ide" like this, it's a simple ion, so just Cl- in this case. Hexahydrate, so .6 H2Os at the end. Ammonium nitrate, ionic, NH4 positive, the complex ion ammonium, and NO3, the complex anion nitrate. And finally, we see our first example of a covalent compound, phosphorus trihydride. I know it's covalent either because I see that prefix trihydride, or because I see that phosphorus, and in this case hydrogen, hydride, they're both nonmetals. So this was molecular compound, or covalent. Phosphorus is P, and then trichloride, so Cl3, PCl3. Now don't worry about these little brackets beside the formulas. Those refer to the phases: solid, liquid, gas, aqueous. I think at room temperature and pressure, technically, ionic compounds at room temperature and pressure are almost always going to be solids. They have high melting points, so they're solids at room temperature. Covalent compounds can be solids, they can be liquids, they can be gases. They're harder to predict what the phase will be. I don't expect you to be able to predict phases at this point, but as a rule of thumb, ionic compounds, salts, they have very high melting points, so almost always, in fact I'm pretty sure always, ionic compounds will be solids at room temperature. I hope that helps. It's a bit of a 30-minute overview. If you missed the lecture, hopefully that helps. Otherwise, it was hopefully a good review for yourself.